This presentation will detail how Raman concatenation can provide both improved range and resolution. It is commonplace in Raman spectroscopy for samples to fluoresce, and this forces the user to trade signal detectability for spectral range. Specifically, as we shift the excitation laser to longer wavelengths, the quantum efficiency of the detector inside of the spectrometer falls off drastically, and this limits our range of detection to the fingerprint region unless a deep-cooled spectrometer is used. Raman concatenation offers a possible solution to this trade-off, and at the same time offers enhanced spectral resolution. So, what is Raman concatenation and how does it work? Well, it is a means of tricking the spectrometer to collect two different Raman spectra that cover the entire spectral range. We do this by using two different excitation wavelengths. In this example, we start off by collecting the fingerprint region of the Raman spectrum by utilizing a 785 nanometer excitation source, and we can see how the light passes through the spectrometer on the left-hand side of the slide. Notice how the longer red wavelengths are not falling onto the detector surface. These represent the longer wave number region of the Raman spectra, known as the hydrogen stretch band. We can correct this issue and allow the spectrometer to capture this longer wave number information by changing the excitation laser wavelength to a shorter wavelength. The spectrometer remains the same, but the light passes differently through it, and it allows us now to collect the longer wave number portion of the Raman spectra. Another way to explain this is to imagine a fixed window frame that represents what the spectrometer sees, in this case the fingerprint region of the Raman spectra. It's important to recognize that spectrometers work in wavelength space, but Raman spectra is displayed in wave number space. Since the wave number space is defined by the excitation wavelength, we can move the wave number space within the window defined by the spectrometer's wavelength range by changing the excitation laser wavelength. So, currently, we see the fingerprint region inside of the window, but the entire Raman spectra is actually being generated by the excitation wavelength. It's just not all contained within the window. Essentially, the longer wave number region, known as the stretch band, is not hitting the image sensor. We can imagine that stretch band as if it is hidden behind the wall next to the window. When we switch from the 785 nanometer excitation wavelength used in the prior example to the 680 nanometer laser, the Raman spectra shifts because it is linked to the excitation wavelength, and the longer wave number spectra moves into the window frame where it can be detected. We now have two distinct Raman spectra, one that used the 785 nanometer excitation wavelength to collect the fingerprint region, and another using the 680 nanometer laser to collect the stretch band region. We can now concatenate these spectra together, and we have the entire Raman spectrum. But wait, there's more. Since the longer wave number spectra has been shifted to a shorter wavelength when we use a shorter wavelength excitation source, we see large gains in quantum efficiency. In this graph, we show the quantum efficiency for several regions of the Raman spectra. Note that when we use a traditional 785 nanometer excitation source, the quantum efficiency is only around 11% at 1050 nanometers, which correlates with the 3200 wave number region. It is only about 1% at 1100 nanometers, which correlates to the 3600 wave number region. But when we use a shorter wavelength of excitation, these bands shift, and we see a huge increase in quantum efficiency as a result. In this case, we see a 7.5x increase in signal when we look at the CH band at 3200 wave numbers, because this now correlates to 870 nanometers. And we see an 81x increase when we look at the water band at 3600 wave numbers, because this now correlates to 900 nanometers. On top of these already big gains, we also get the frequency to the fourth power advantage when we switch to the shorter wavelength of excitation. And we also get this with no increase in noise, because we have not changed the integration time on the spectrometer. So, now that we have an understanding of how Raman concatenation works and the signal enhancement we expect to see in the stretch band, let's look at some examples. In this chart, we show the Raman spectra for cyclohexane. This data was taken with a high-performance spectrometer capable of collecting Raman spectra up to about 3500 wave numbers. The brown-colored plot represents the traditional Raman spectra collected using a 785 nanometer excitation wavelength, and the red spectra represents the hydrogen stretch band collected on the same spectrometer with the same integration time, but using the 680 nanometer excitation wavelength in concatenation mode. In the inset region, we can see the tremendous increase in signal obtained, but we can also see that the spectral resolution is enhanced as well, since we can discriminate the small Raman peaks at 2930 wave numbers. Here are two more examples. On the left, we detail how the concatenated Raman signal shown in red is capable of detecting the NH band in urea as compared to the traditional approach. On the right-hand side, we can see how the water band is cut off in the traditional collection approach, but it is clearly detectable using the Raman concatenation approach. In summary, Raman concatenation is an innovative technique that can help spectroscopists avoid having to choose between range and resolution, and it offers an advantage that the signal in the stretch band is enhanced as compared to the traditional approach due to the increase in sensor quantum efficiency and the frequency to the fourth power advantage gained by using a shorter excitation wavelength.